So, take a breath. Just notice it, the air moving in, the weight of your body wherever it's resting right now, the small sounds of the room around you. This exact second. This is the only now you have direct access to. But here's the strange, quiet question we're going to spend the next little while sitting inside. Is this the only now there is? Right this moment. Is there another version of this same instant happening somewhere else, in some other place you'll never see, where things went slightly differently, or maybe not differently at all? That probably sounds like science fiction. It's not. Or, well, it's not only science fiction. It's something stranger than that, which is that this idea, this unsettling suggestion that there might be other universes, other versions of now, keeps showing up as an honest, almost accidental byproduct of physics that's been tested, measured, confirmed 1,000 different ways. Nobody set out looking for parallel universes. That's what makes this whole thing so strange. Serious, careful, skeptical scientists, working on completely unrelated problems, in completely different decades, using completely different tools, kept independently arriving at the same strange destination. That's the part worth sitting with. Not one idea, dressed up 5 different ways. 5 separate roads. 5 different sets of footprints, all ending up in roughly the same place. Tonight we're going to walk those roads slowly, one at a time. There's a physicist named Max Tegmark who spent years organizing this whole tangle of ideas into something like a map, for levels, each one stranger and more speculative than the last. We'll use his map as our spine tonight, level by level, no rushing. We'll start with the universe of infinite space, and the almost dizzying thought that somewhere out there, impossibly far away, there might be another version of this exact room, another version of you, having this exact thought. Then we'll drift into bubble universes and a physicist scribbling in a notebook late one night in 1979, writing down what he called a spectacular realization. Then quantum mechanics, and a young graduate student named Hugh Everett who suggested, quietly, almost apologetically, that the universe never really has to choose, that every possibility just happens, somewhere. And then, right at the edge of what physics can even still call itself physics, an idea so strange that most scientists consider it philosophy, that mathematics itself might be the deepest fabric of reality, and that any structure math can consistently describe already exists, somewhere, in whatever way existing means out there. Here's the thing I want to tell you before we go any further, because I think it matters more than any of the specific ideas. You are allowed to be confused by this. Confusion isn't you failing to keep up. Confusion is the correct, honest, appropriate response to material like this. Einstein was confused by quantum mechanics. Genuinely, deeply unsettled by it, right up until the end of his life. Niels Bohr was confused, in a different direction, and he and Einstein argued about it for decades, politely, stubbornly, without either one giving ground. Hugh Everett, the man who came up with one of tonight's biggest ideas, spent years being quietly dismissed, and it's not clear even he was fully at peace with what his own equations seemed to be telling him. So if some part of this washes past you tonight, if you find yourself drifting, losing the thread, that's fine. That's more than fine. Let it happen. The ideas will still be here tomorrow, and the day after that, sitting patiently, waiting for you to come back to them whenever you want to. Tonight isn't a test. There's nowhere you need to arrive. Just listen, and let your mind do whatever it wants to do with all this. Drift if you drift. Sleep if you sleep. Let's slow down, and start right at the beginning, with a word. The word is universe, and it used to be a much smaller, much more confident word than it is now. For most of human history, universe simply meant everything, and everything wasn't actually all that much. Go back a few thousand years and the universe, for most people, was the Earth, a dome of sky sitting over it, some wandering lights people eventually figured out were planets, and a scattering of fixed stars pinned somewhere further out, close enough together that they seemed to belong to the same single shell of sky. That was it. That was everything there was. The universe wasn't some vast, humbling concept back then. It was almost cozy, almost knowable. You could imagine the whole thing, more or less, the way you might imagine the layout of a house you've lived in your whole life. And then, slowly, embarrassingly, that cozy little universe kept turning out to be wrong. Not wrong the way a simple mistake is wrong, but wrong in this specific, recurring way, where every single time humanity thought it had finally found the edge, the actual boundary, the true size of everything. It turned out we'd only found the edge of what our instruments happened to be able to see. Not the edge of the universe, the edge of our looking. Copernicus moved the Earth from the center of everything to just one planet, orbiting, unremarkable. That alone was an enormous demotion, and plenty of people, powerful people, were furious about it. But even after that shift, most educated people still assumed the stars themselves marked some kind of outer boundary, that beyond the stars there was, well, nothing. Or God. Or something that wasn't really more universe, just an edge. Let's slow down for a moment on just how old this particular argument actually was, because it didn't start with Hubble. Back in the 1750s, long before anyone had a telescope powerful enough to settle the question either way, the philosopher Immanuel Kant speculated, almost as a pure thought experiment, that some of these faint, fuzzy patches of light astronomers had been cataloging might actually be entire separate systems of stars, island universes, as he called them, existing far outside our own. It was an elegant guess, resting on almost no direct evidence at all, and for well over a century afterward, nobody had the tools to confirm or deny it. By the early 20th century, the argument had become sharp enough that it produced something astronomers still refer to as the Great Debate, a formal public exchange held in 1920 in Washington between two astronomers, Harlow Shapley and Heber Curtis, who disagreed directly on this exact question. Shapley argued these spiral nebulae were relatively small, nearby objects, comfortably contained within one large Milky Way that constituted essentially the whole universe. Curtis argued the opposite, that at least some of these nebulae were vast, separate galaxies in their own right, sitting at enormous distances outside our own. Neither side had quite enough evidence to settle it decisively that day. The debate ended, honestly, in a draw, each side having made reasonable points the available data of 1920 simply couldn't yet adjudicate. Then, in the 1920s, an American astronomer named Edwin Hubble, working at the Mount Wilson Observatory up in the mountains above Los Angeles, pointed the largest telescope on Earth at the time at a smudgy little patch of light in the sky called Andromeda. For years, astronomers had argued about what these fuzzy little smudges actually were. Some people called them spiral nebulae, and assumed they were just clouds of gas, sitting somewhere inside our own galaxy, the Milky Way, which most people still assumed was the entire universe. One single island of stars, floating in an otherwise empty void. Hubble did something patient and careful. He found a particular kind of star inside Andromeda, a star whose brightness pulses in a very specific, very reliable rhythm. The kind of star astronomers can use almost like a lighthouse with a known wattage, letting you calculate distance just from how bright it appears to be. And when Hubble ran the numbers, they came out enormous. Not somewhere else in our galaxy enormous. Millions of light years enormous. Andromeda wasn't a gas cloud drifting inside the Milky Way. Andromeda was its own galaxy, its own vast island of hundreds of billions of stars, sitting almost unthinkably far outside our own. The Milky Way, the thing people had quietly assumed was the whole universe, all of it, turned out to be one galaxy. Just one. Among what we now know are something like 2 trillion others, scattered out into the dark in every direction we've ever managed to look. I want you to just sit with that update for a second, because it happened to humanity almost within living memory, within your grandparents' lifetime, maybe your own parents. For essentially all of human history, the universe meant our galaxy, full stop, and then in the 1920s that turned out to be embarrassingly, wonderfully wrong, and it turned out to be trillions of times bigger than anyone had allowed themselves to imagine. And Hubble wasn't finished. A few years later, continuing to study these newly discovered galaxies, he noticed something else, something even stranger. The light coming from almost every distant galaxy was shifted slightly toward the red end of the spectrum, a phenomenon called redshift, and the further away a galaxy was, the more its light was shifted. The most natural explanation, the one that held up under decades of further testing, was that these galaxies weren't just sitting out there at a fixed distance. They were moving away from us, and the farther ones were retreating faster than the nearer ones, in exactly the pattern you'd expect if space itself were stretching uniformly in every direction, carrying galaxies apart the way raisins in a rising loaf of bread drift apart from each other as the dough itself expands. none of them moving through the dough so much as being carried along by it. This was the first real observational evidence for what we now call the expanding universe, and run backward far enough in time. It's also the evidence that eventually led to the Big Bang model itself, the idea that everything was once compressed into an extraordinarily hot, dense state, expanding and cooling ever since. Even this, notice, followed the same quiet pattern. Careful measurement, patiently taken, revealing something about the true scale and behavior of everything that intuition alone never would have guessed. And here's the pattern I want you to notice, because it's going to repeat itself again and again tonight. Every time humanity thought it had found the true edge of everything, it later turned out we'd only found the edge of what we could currently detect. The dome of stars wasn't the edge of the universe, it was the edge of naked eye astronomy. The Milky Way wasn't the edge of the universe, it was the edge of what telescopes in the 1800s could resolve. And tonight, we're going to ask, gently, honestly, without any hurry to answer it, what if the same pattern is still happening? What if the edge of the observable universe, the one modern telescopes still can't see past, isn't the edge of everything either? What if it's just, once again, the edge of our looking? That question, sitting quietly underneath all four of tonight's levels, is really what this whole episode is about. There's one more thing worth sitting with before we start walking through the levels themselves, and it's this. Each time our sense of everything got bigger, it wasn't because someone sat down and imagined a bigger universe out of pure creativity. It was because someone built a slightly better tool, a slightly sharper lens, a slightly more patient method of measurement, and pointed it a little further than anyone had managed to point anything before. Galileo's little telescope showed moons orbiting Jupiter, proving not everything circles the Earth. Herschel's larger telescopes, a couple centuries later, started resolving individual stars inside those fuzzy nebulae, hinting they might be something more than clouds. And Hubble, with the largest telescope of his era, finally had enough resolving power to separate out individual pulsing stars inside Andromeda, stars whose brightness told him, unmistakably, just how far away that smudge of light really was. So notice, gently, that the story of the universe getting bigger isn't really a story about wild imagination outrunning evidence. It's almost the opposite. It's a story of evidence, patiently, slowly, outrunning our imagination again and again, forcing each generation to accept a universe larger and stranger than the one they'd grown comfortable with. That's the spirit we're going to carry with us tonight, through all four levels. Not what can we imagine, but what does the math, taken seriously, patiently, honestly, actually seem to be telling us, even when what it's telling us feels too large to hold comfortably in one sitting. Let's start with the gentlest version of that question, the most conservative one, the one that requires the fewest leaps of imagination. This is what Tegmark calls level 1. And the idea, at its heart, is almost embarrassingly simple once you say it out loud. It's just this: what if space keeps going, past the point where we can see it? When we talk about the observable universe, we don't mean the whole universe. We mean the part of it whose light has had enough time to reach us since the beginning. Light is fast, but it isn't infinite, and the universe is only about 13.8 billion years old, so there's a hard limit on how far away something can be and still have its light arrive here by now. That limit works out to a bubble around us roughly 93 billion light-years across. Once you account for the fact that space itself has been stretching the whole time that light's been traveling. That's the observable universe. That's the bubble we can, even in principle, ever get information from. But notice what that number actually is. It's not a measurement of how big the universe is. It's a measurement of how far light happens to have traveled since the beginning, from wherever we happen to be standing. It's a horizon, not a wall. And a horizon, if you've ever stood on a beach or a wide-open plain, isn't a place. It's just the limit of your seeing. If you walk toward it, it would keep receding, revealing more beach, more plain, further out, forever, as far as you kept walking. Here's an image I want you to hold on to, because we're going to come back to it. Imagine an ant, standing on an absolutely enormous, endless beach. Flat, uniform, sand in every direction, no edges anywhere the ant can detect. But the ant has terrible eyesight. It can only see a few inches around itself. From where the ant is standing, that little visible patch of sand is its entire observable world. As far as the ant is concerned, functionally, that patch is the universe. But we, standing back, watching this ant on its beach, know something the ant doesn't. We know the beach keeps going, grain after grain after grain, in every direction, long after the ant's tiny visible patch runs out. And here's the detail that makes this image more than just a cute illustration. The ant isn't wrong, exactly, to call its little visible patch the universe. Given its eyesight, given the tools available to it, that patch really is the entirety of what it can ever meaningfully investigate, measure, or reason about directly. Its mistake, if you can even call it a mistake, isn't in the measurement. It's in assuming that the boundary of its measurement is the same thing as the boundary of what exists. That's a distinction worth sitting with gently, because it's exactly the distinction at the heart of tonight's whole first level. Our observable universe, that 93-billion light-year bubble, is genuinely, honestly, the entirety of what we can investigate. Every telescope, every measurement, every fact we've ever confirmed about the cosmos lives inside that bubble. Nothing about tonight's reasoning asks you to distrust any of that. It only asks you to notice, gently, that the edge of our measuring instrument was never promised to be the edge of everything there is. We are, in a very real sense, that ant. Our observable universe, that 93-billion light-year bubble, might simply be our visible patch of sand. And if the beach really is endless and reasonably uniform, the same rules of physics and the same rough distribution of matter applying everywhere, not just here, then something quietly extraordinary follows almost automatically from ordinary statistics. Let's slow down here, because this next part sounds outrageous, and I want to walk through it carefully instead of just asserting it. Matter, at the smallest scales, is made of particles, and particles can only be arranged in so many distinct ways within any given volume of space. It's an enormous number, don't get me wrong, an almost incomprehensibly large number, but it is, crucially, a finite number. There is some upper limit on how many different ways you could arrange all the particles inside, say, a region the size of our observable universe. Here's a smaller, more familiar version of the same logic, just to get a feel for it before we scale it up to something as vast as the universe. Take an ordinary deck of 52 playing cards and shuffle it thoroughly. The number of possible orderings that deck could end up in, though enormous, is still finite, a specific, countable number. If you had, somehow, an infinite number of decks and shuffled every single one of them, it wouldn't just be likely that some of those decks landed in the exact same order as each other. It would be certain, mathematically guaranteed, that the same specific ordering showed up again and again, infinitely many times, simply because you're placing a finite number of possible outcomes into an infinite number of trials. Nothing mysterious is happening there. It's just ordinary statistics, taken to its logical conclusion. The reasoning behind an infinite, repeating universe works exactly the same way, just with an almost unfathomably larger deck and stretches of space standing in for shuffles. Now, if space truly is infinite, or even just vastly larger than our observable patch, and if the same basic physics applies everywhere within it, then you have a finite number of possible arrangements being repeated across an infinite, or near infinite, amount of space. And when you take a finite set of possibilities and repeat the process of arranging things an effectively infinite number of times, every possible arrangement doesn't just get a chance to happen. It happens infinitely many times. Which means, and I want to say this slowly, because it deserves to be said slowly, if this reasoning holds, somewhere out there, unthinkably far away, there is a region of space arranged almost exactly like the one you're in right now. Not metaphorically similar. Arranged the same way, down to the particle. Which would mean there's a version of this room. A version of the specific chair or bed or floor you're on right now. A version of you, hearing words very much like these, drifting towards sleep in very much the way you might be right now. I know how that sounds. I know it sounds like the kind of thing that shouldn't be treated as a serious scientific claim, and I want to be honest with you about exactly how much weight this idea can actually hold, because that matters more than the eeriness of it. This isn't built on some elaborate speculative model. It rests on two much smaller, much more testable assumptions. First, that space is at least extremely large, plausibly infinite. extending well beyond what we can see. Second, that it's roughly uniform out there, obeying the same physics we observe locally, rather than turning into something bizarre and unrecognizable past our horizon. And here's the honest, grounding part. Those two assumptions aren't just hopeful guesswork. They're supported by real, careful measurements. Satellites like WMAP, and later the Planck satellite, spent years mapping the cosmic microwave background, this faint, ancient afterglow of light left over from when the universe was only a few 100,000 years old. And one of the things that light lets scientists measure with real precision is the overall geometric shape of space itself. Is it curved, like the surface of a sphere, where if you traveled far enough in one direction you'd eventually loop back around to where you started? Or is it open, curving the other way, like a saddle? Or is it flat, the ordinary geometry most of us grew up learning, where parallel lines never meet and space just keeps extending? Let's slow down on how you'd even measure something like that, because it's a lovely piece of reasoning in its own right. The cosmic microwave background contains tiny, faint variations in temperature, patches slightly warmer or cooler than their surroundings, laid down when the universe was still young. Physicists know, from careful theoretical modeling, roughly how large these patches should physically have been at that early moment in real physical terms. And because we also know how far away that ancient light has traveled to reach us, there's a straightforward bit of geometry available. If you know an object's true physical size and the angle it appears to take up in the sky from where you're standing, you can work out whether the space the light traveled through was flat, or curved one way, or curved the other way. The exact same geometric reasoning you'd use to notice something was wrong if a familiar-sized object looked strangely warped or distorted from a particular vantage point. When WMAP, and later the more precise Planck satellite, carried out this measurement across the whole sky, the answer came back flat, again and again, to within about 0.5%, an extraordinarily tight constraint for something this fundamental. The measurements, again and again, keep coming back the same way. Flat. Or at least, flat within the margin of error we're currently capable of measuring, which is remarkably tight. And flat space, unlike curved space, has no natural mechanism to close back in on itself. Flat space, left to its own devices, just keeps going, which is exactly the kind of space where this endless beach reasoning applies. So this first level, this softest, most conservative suggestion of parallel universes, isn't really asking you to believe in some new kind of physics at all. It's asking you to take two things you already, provisionally, believe, space being large and space being roughly uniform, and simply follow them a little further than we usually bother to. No wormholes. No new dimensions. No exotic quantum weirdness. Not yet, anyway. Just space, doing what space does, for longer than we normally think about, and the strange, quiet consequence of that. Let's slow down even further here, because there's a natural question that probably occurred to you already, and it deserves a real answer rather than a wave of the hand. How far away would this repeating room actually be? And the honest answer is, absurdly, almost meaninglessly far. Estimates for the distance at which you'd expect to find an exact repeat of our observable universe, given the finite number of particle arrangements involved, come out to distances that dwarf the observable universe itself by mind-bending factors, numbers with so many zeros that writing them out doesn't really communicate anything useful anymore. It's not somewhere out past Andromeda. It's not even remotely in that neighborhood. It's a distance so enormous that the number of zeros involved is itself larger than the number of atoms in our entire observable universe. This isn't a nearby neighborhood we might someday visit. It's a mathematical consequence of infinite, uniform space, sitting at a distance that will never, under any circumstances, be reachable, or observable, or testable in any direct way. Not now, not ever, no matter how advanced our instruments become. And that's worth acknowledging honestly, because it means level 1 sits in an interesting, slightly uncomfortable position. The reasoning behind it is about as solid, as conservative, as anything in this whole episode, resting on assumptions we've genuinely measured. But the conclusion itself, that repeating room, that other version of you, is something we will never, even in principle, be able to go check. It's not observationally testable in any direct sense, even though the logic leading to it is built from things that are. That tension between solid reasoning and untestable conclusions is actually going to be a running theme tonight, showing up again and again as we go further out along each of these 4 levels. Let's also gently address something that tends to nag at people the first time they hear this idea, which is a kind of instinctive worry about free will or meaning, or whether any of this makes your choices matter less. If there's a version of you out there, unimaginably far away, having made every possible variation of choices you could have made, does that make your specific choices here, tonight, in this room, feel smaller somehow? I'd gently push back on that instinct. That other version, if it exists at all, is causally disconnected from you completely. Nothing you do here reaches it. Nothing it does reaches you. In every way that matters to your actual, lived experience, this is still the only life you have, the only choices you get to make, the only now you get to act inside. The vastness of an infinite beach doesn't make your particular patch of sand matter any less. If anything, it's the only patch you'll ever get to stand on, which might be reason enough to treat it gently. You don't have to hold on to any of this too tightly tonight. Just let it sit there, gently, like a stone dropped into still water. Somewhere out past the edge of what we'll ever see, more sand, more beach. Maybe, somewhere in all that sand, another version of this exact, quiet moment. And then let's move a little further, because level 1, it turns out, was really just the doorway. Let's talk about bubbles now, and about a young physicist, working late one night in December of 1979, who thought he'd stumbled onto something important enough that he wrote it down in his notebook with a heading he must have known, even at the time, sounded a little dramatic. His name was Alan Guth. In the late 1970s, he was a postdoctoral researcher, bouncing between temporary positions, the kind of early career uncertainty a lot of brilliant physicists go through before anyone knows their name. He'd been thinking about a particular problem in cosmology, something called the horizon problem, which is this puzzling observation that different, extremely distant regions of the universe, regions so far apart that light couldn't possibly have traveled between them in the time since the Big Bang, somehow still ended up looking almost identical in temperature. Like 2 rooms on opposite ends of the universe, with no way to have ever communicated with each other, that nonetheless came out at almost exactly the same temperature. It's the kind of coincidence that makes a careful physicist suspicious. Coincidences that large usually mean you're missing a mechanism. Let's picture that December night for a moment, slowly, because it's a nice, human image to hold on to. Guth was still relatively unknown at the time, working through calculations in a notebook, the way physicists often do, half thinking out loud on paper. And at a certain point in his notes, he drew a box around a paragraph, and above the box, he wrote, almost as a private note to himself, spectacular realization. Not a formal announcement to the world. A private, excited moment, jotted down for no one but himself. The kind of small, human gesture that ends up meaning something only in retrospect, once the rest of the world catches up to why it mattered. Guth's answer, the idea that came to him and that he underlined in his notebook that December night, calling it a spectacular realization, was this: what if, in an unimaginably brief fraction of a second right after the Big Bang, the universe underwent an incredibly violent, exponential burst of expansion? Not the gentle, gradual cosmic expansion we still see stretching space today, but something far more explosive, space doubling in size, then doubling again, then again, over and over, in a sliver of time too short to easily put into words, before settling back down into the calmer expansion we observe now. He called this brief, violent burst inflation, and it elegantly solved the horizon problem, because those distant regions that now seem too far apart to have ever touched actually had touched, back before inflation blew them impossibly far apart from each other. There's something worth sitting with about Guth's own situation at the time, because it adds a certain gentle humanity to the story. He was in his early 30s, and by his own later account, he'd spent years drifting between short-term postdoctoral positions, at Cornell, at Princeton, at other institutions, without ever quite landing the kind of secure, permanent post that lets a young physicist feel settled. He'd worked on several other projects before this one that hadn't gone anywhere significant. Inflation, this idea he stumbled into almost as a side calculation while thinking about an unrelated problem in particle physics, ended up being the thing that finally, decisively, changed the trajectory of his career, earning him a permanent position at MIT not long after, and eventually, decades later, a share of some of physics' most prestigious prizes. It's a nice reminder that some of the biggest ideas in this whole story didn't come from towering, already famous figures working with total confidence. They came from someone in an uncertain, unglamorous stretch of an early career, quietly doing the math, and getting, as he put it himself, spectacularly lucky in exactly the way careful, patient work sometimes turns out to be lucky. That idea alone would have been a significant contribution to cosmology. But it's what happened next, in the hands of another physicist, a Russian-American named Andrei Linde, that starts pulling us toward tonight's second level. Linde was working in the Soviet Union in the early 1980s, developing his own independent versions of inflationary theory alongside Gauss's, part of a small international community of physicists on both sides of the Cold War divide, who were quietly converging on very similar ideas about the early universe around the same time, largely through published papers rather than direct collaboration, since travel and communication between Soviet and Western scientists during this period was often difficult and restricted. Linde later emigrated to the United States in the late 1980s, eventually taking a position at Stanford, where he continued refining these ideas for decades. It's a small, human detail worth sitting with, that some of tonight's biggest cosmological insights were developed independently, in parallel, by people separated by an actual geopolitical divide, each arriving at strikingly similar conclusions without much ability to directly compare notes along the way. Linde asked a question that, once you hear it, seems almost obvious, and yet nobody had quite pushed on it the way he did. If inflation is this violent, unstable process, driven by a field of energy that eventually decays and settles down, calming into the ordinary universe we observe, then does that decay actually have to happen everywhere at exactly the same moment? Or could different regions decay, different regions calm down and stop inflating at different times? Linde's insight, refined through the 1980s, was that inflation likely doesn't stop everywhere at once. In fact, it may never stop everywhere. It might only stop locally, in patches, while continuing to boil onward everywhere else. Picture a pot of water at a rolling boil. Most of the water is churning, chaotic, still boiling. But here and there, a bubble forms, a little pocket where the water calms, where the energy locally settles into something quieter. Our own universe, in this picture, is one such bubble. A local patch where inflation ended, where things calmed into the stable, structured cosmos we can observe, floating inside a vastly larger, eternally boiling background of still inflating space, a background dotted with countless other bubbles, other calmed regions, other universes, each one potentially having its own version of physics, its own version of the fundamental constants, forming and drifting apart forever, in every direction, without end. This is level 2. Not infinite copies within our universe, like level 1, but an endless, actively bubbling multiverse birthing entirely separate universes, each one its own bubble in a boiling pot that never fully cools. Let's slow down on one detail here that people sometimes trip over, because it's genuinely counterintuitive. You might expect that if the background is always inflating and only occasionally calming into bubbles, then eventually all the inflating background would get used up, converted entirely into bubbles, the way a pot of water eventually finishes boiling away completely. But eternal inflation, mathematically, doesn't work that way. The inflating background expands so much faster than any individual bubble can grow within it that the total volume of still inflating space actually keeps increasing overall, forever, even as new bubbles keep constantly forming inside it. It's less like a pot finishing its boil, and more like a pot that's somehow expanding faster than it's boiling. So no matter how many bubbles rise up, the still boiling water underneath just keeps growing, without limit. That's part of why Linde called it eternal. Not eternal in the sense of lasting a very long time. Eternal in the sense of never actually finishing anywhere, even in principle. Here's where things get even stranger, and where a whole different branch of physics unexpectedly walks in through the same door. There's a piece of theoretical physics called string theory, which tries to describe all the fundamental particles and forces not as points, but as unimaginably tiny vibrating strings, with different vibration patterns giving rise to different particles, the way different notes come from different vibrations of a guitar string. One of the strangest requirements of string theory, mathematically, is that its equations only work cleanly if the universe has more spatial dimensions than the three we actually experience, typically 6 or 7 additional ones, curled up so tightly, so impossibly small, that we'd never notice them in ordinary life. The way a long garden hose looks like a simple, one-dimensional line from far away, even though its surface actually wraps around a small, hidden second dimension if you looked closely enough. String theory doesn't just describe one possible universe. It describes an enormous landscape of mathematically consistent possible universes, differing in things like the exact shape those extra curled-up dimensions take, or the specific values of fundamental constants like the strength of gravity or the mass of an electron, each different shape and configuration effectively producing its own distinct version of physics. A physicist named Leonard Susskind, working through the implications of this landscape in the early 2000s, estimated the number of distinct possible configurations at something like 10 to the 500th power, a number so large it isn't really meant to be pictured, only acknowledged. Let's slow down on that number for just a moment, gently, because it's easy to let a phrase like 10 to the 500th slide past without really registering it. The number of atoms in our entire observable universe is estimated at around 10 to the 80th. 10 to the 500th isn't a little larger than that. It isn't 1,000 times larger or 1,000,000 times larger. It's larger by a margin that dwarfs the very idea of larger, a number with roughly 420 more zeros tacked onto the end than the number of atoms in everything we can see. Susskind himself, and other physicists working on this landscape, sometimes describe it less like a list of options and more like an enormous, largely unexplored territory, a mathematical wilderness where most regions have never been visited by any calculation at all, simply because there are too many of them to check. Our own universe, on this picture, is just one specific point, one specific setting, somewhere inside that unfathomably large wilderness. And here's the bridge. If Linda's eternal inflation is constantly popping off new bubble universes, and if string theory's landscape says there are roughly 10 to the 500th different possible settings those universes could land on when they calm down, then eternal inflation gives you the mechanism, and the string landscape gives you the menu. Countless bubbles, endlessly forming, each one randomly settling into one of an almost unfathomable number of possible configurations of physics. Before we get to the specific prediction, let's slow down on the general style of reasoning behind it, because it's a little unusual, and it helps to understand the shape of the argument before seeing it applied. This kind of reasoning is usually called anthropic reasoning, and the core idea is almost embarrassingly simple once it's stated plainly. Whatever universe we happen to find ourselves observing from must, necessarily, be a universe capable of producing observers in the first place. That sounds almost circular, but it isn't quite, because it lets you make a real prediction. If there's a whole landscape of possible universes out there, most of them hostile to life, only a narrow slice of them capable of producing anything like stars, chemistry, or physicists, then whichever universe we happen to be sitting in should fall somewhere within that narrow, life-permitting slice, almost by definition, regardless of how rare that slice happens to be among all the possibilities. It's less a statement about how the universe works, and more a statement about the kind of place any observer, by simple necessity, has to be standing in order to ask the question at all. This connects to something that happened in 1987, when physicist Steven Weinberg made a genuinely uncomfortable and genuinely testable prediction using exactly this style of reasoning. There's a quantity in cosmology called the cosmological constant, related to a kind of energy woven into empty space itself, energy that pushes the universe to expand. For decades, physicists mostly assumed this constant should be either exactly zero, for some deep symmetry reason we hadn't found yet, or else enormous, driven by expected contributions from particle physics. Weinberg, working from the multiverse picture, made a different argument. If there really are countless universes, each with a randomly different value for this constant, then most of them would have values either so large they'd tear themselves apart before galaxies or stars or anything resembling us could ever form, or so negative they'd collapse back on themselves almost instantly. Only a narrow, unusual range of values would allow a universe stable enough, patient enough, to produce galaxies, stars, planets, chemistry, life, physicists capable of measuring a cosmological constant at all. Weinberg predicted that whatever value we eventually measured should fall within that narrow, life-permitting range, and predicted it should be small, but not exactly zero. In 1998, observations of distant supernovae confirmed the universe's expansion actually is accelerating, driven by a cosmological constant that turned out to be small, positive, and non-zero, sitting close to the range Weinberg had described roughly a decade earlier. It's the kind of prediction that makes even skeptical physicists sit up a little straighter. I want to be fair here, though, and give you the honest pushback too, because that's part of taking this seriously rather than treating it like a magic trick. Plenty of thoughtful physicists, people like Paul Steinhardt, one of the original architects of inflationary theory himself, have raised a serious concern about this whole picture. If there's a landscape of 10 to the 500th possible universes, and an endless bubbling process constantly generating new ones, then almost any observation you could possibly make is predicted by the theory somewhere in that landscape. And a theory that can comfortably explain any possible result starts to look less like a scientific prediction and more like an excuse. That's the falsifiability critique, and it's a fair one that Level 2 has never fully answered. We'll come back to this question, honestly, later tonight, because it matters, and I don't want to pretend it's been settled when it hasn't. For now, just let this second level settle in gently, the way the first one did. Not infinite copies scattered through one endless space, this time, but an endless, actively boiling process, quietly generating universe after universe after universe, each one its own bubble, most of them, statistically, uninhabitable, a rare few calm enough, patient enough, lucky enough, to grow something like a galaxy. Something like a star. Something like tonight. Let's pause here for just a moment, gently, before we go any further, because we've covered a lot of ground already, and I want to give you a chance to just breathe with it for a second rather than rushing straight into the next idea. So far, we've talked about space that might repeat itself endlessly, if it's large and uniform enough. And we've talked about an inflating background that might never stop bubbling, spinning off universe after universe, each one landing somewhere on an almost incomprehensibly vast landscape of possible physical laws. Two separate ideas, from two separate corners of physics, both quietly pointing toward the same strange conclusion, that everything might be far larger and far stranger than the one universe we happen to be sitting inside of. But here's where things shift into something even more intimate, something that isn't happening unthinkably far away at all, but is happening. If it's happening, right here, inside this room, inside you, in this exact instant. Because our third level isn't about space stretching outward into some distant, unreachable elsewhere. It's about a branching that some physicists think might already be occurring, silently, constantly, every single time a quantum event resolves one way instead of another, anywhere, including right now. Let's slow all the way down now, because this next level is, in a lot of ways, the emotional heart of tonight's whole story. And it's not really a story about galaxies or bubbles or inflation at all. It's a story about a quiet, shy graduate student and a thesis almost nobody wanted to hear and what happened to him afterward. His name was Hugh Everett III. In the mid-1950s, he was a doctoral student at Princeton, working under one of the most respected physicists of the era, John Wheeler. It's worth knowing a little about Wheeler himself here, gently, because it explains some of what happens later in this story. Wheeler was, by this point, already a towering figure in physics, someone who had worked directly with Niels Bohr years earlier, helping develop some of the foundational theory behind nuclear fission, and who would later become famous in his own right for popularizing the term black hole. He was deeply respected, deeply embedded in the physics establishment, personally close with Bohr, and by most accounts, a generous, encouraging mentor to his students, genuinely excited by unconventional ideas. But he was also someone who cared, quite understandably, about the reputations of the students under his direct supervision, and about not needlessly antagonizing the most powerful figures in his field. That combination, genuine excitement about a radical idea, paired with real caution about how it would land, shapes almost everything that happens to Everett's thesis over the following few years. And the problem Everett had become fixated on wasn't cosmology at all. It was something smaller, stranger, and in some ways even more unsettling. It was the measurement problem in quantum mechanics. Here's the problem, and let's take it slowly, because it's genuinely one of the strangest things in all of physics. There's a simple experiment, one of the oldest and most famous in all of quantum physics, that makes this concrete. Take a barrier with two thin, parallel slits cut into it, and fire individual particles, electrons, say, one at a time, toward it, with a detector screen on the far side. If electrons behaved like tiny ordinary bullets, you'd expect two clean bands to build up on the screen over time, one behind each slit. That's not what happens. Instead, even firing the electrons one at a single, isolated time, with long gaps between each one, an interference pattern slowly builds up on the screen, alternating bands of many hits and almost no hits, the exact pattern you'd expect from two overlapping waves interfering with each other, not two streams of separate little particles. Somehow, each individual electron seems to behave as though it passed through both slits at once, interfering with itself, even though only one electron went through at a time. And here's the part that unsettled physicists even further. If you set up a way to check which slit each electron actually went through, the interference pattern vanishes completely, and the electrons suddenly do behave like ordinary bullets again, landing in two simple bands. The mere act of checking, of gaining that information, seems to change the outcome. At the smallest scales, particles don't behave the way ordinary objects do. Instead of having one definite position, or one definite spin, or one definite anything, a particle's properties are described by something called a wave function, which represents a spread of different possibilities, all mathematically present at once, each with a certain probability attached to it. This isn't just physicists being unsure and needing to gather more data. The equation strongly suggests the particle genuinely doesn't have a single definite value until, somehow, it does. And that somehow is the whole problem. Because the moment you measure a particle, the moment you actually look, you never see a spread of possibilities. You see one specific outcome, one position, one spin, just one. The other possibilities, mathematically, seem to simply vanish. Physicists call this collapse of the wave function, and for decades, the dominant explanation, developed mostly by Niels Bohr and his colleagues in Copenhagen, essentially treated this collapse as a fundamental, unexplainable rule of nature. Measurement happens. The wave function collapses. Only one outcome survives. Don't ask why, or how, or what happens to the other possibilities. That's simply not a question physics answers. Just accept it and move on to calculating things, which the theory is spectacularly good at doing, even without ever explaining this part. A lot of physicists were satisfied with that. Bohr certainly was. But a lot of physicists weren't, either, including Einstein, who famously never fully made peace with this framework, and a young graduate student named Hugh Everett, who found himself deeply bothered by a specific, nagging question. If quantum mechanics is really the fundamental theory of everything, and if measuring devices and the physicists using them and their brains are themselves ultimately made of the same particles obeying the same quantum rules, then why should the act of measuring be special at all? Why would the universe suddenly, mysteriously suspend its normal quantum behavior the instant a measurement happens, collapsing everything down to one outcome, rather than just continuing to follow its own equations, the same way it does for everything else? Everett's answer, developed in his 1957 doctoral thesis, was almost unbearably elegant and almost unbearably strange. What if there simply is no collapse? What if the wave function never actually shrinks down to one outcome at all? What if, instead, every possible outcome keeps happening, all of them, simultaneously, but the universe itself quietly splits, branches, so that each outcome plays out in its own separate, non-communicating version of reality? Let's make this concrete, slowly, with one simple example, because the idea is much easier to hold on to with something specific in front of it than with abstract talk of wave functions. Imagine a single radioactive atom, one that has exactly a 50% chance of decaying within the next hour. This isn't a hypothetical simplification, either. Real radioactive isotopes genuinely do decay according to these exact kinds of odds, a fixed probability per unit of time, with no way, even in principle, to know in advance which individual atom will decay first and which will hold together longer, a genuine randomness sitting at the very foundation of the physics, not just a randomness caused by our own ignorance. According to ordinary quantum mechanics, before you check, that atom exists in a mixture, a superposition, of decayed and not decayed, both possibilities mathematically present at once. In the traditional Copenhagen picture, the moment you check, this superposition collapses, and you get one answer: decayed or not decayed, with the other possibilities simply gone, erased from reality. In Everett's picture, something different happens. Both outcomes occur. The universe, in that instant, branches into two, almost perfectly identical, non-interacting versions. In one branch, the atom decayed, and you observe that. In the other branch, the atom didn't decay, and a different version of you observes that instead. Neither version of you experiences the branching itself. From the inside, from your own perspective, it simply feels like one single, definite outcome happened, because you only ever experienced the branch you happened to be inside. But according to Everett's math, the other branch, the other version of that moment, and the other version of you, is just as real, just as physically valid, sitting alongside yours, forever unable to communicate back. This reframes one of the most famous thought experiments in physics, Schrödinger's cat, in a way that's honestly a lot gentler than how it's usually explained. It's worth knowing, first, that Erwin Schrödinger didn't invent this thought experiment to celebrate quantum weirdness. He invented it in 1935 specifically as a kind of complaint, a deliberately absurd example meant to highlight what he saw as a flaw in the Copenhagen interpretation, a way of saying, essentially, look how ridiculous this framework becomes once you scale its logic up from a single particle to something as ordinary as a cat. He wasn't proposing this as something he believed was actually happening. He was trying to make Bohr's picture look uncomfortable by extension. Schrödinger proposed a sealed box containing a cat, along with a mechanism that kills the cat if a certain radioactive atom decays. Under standard quantum mechanics, before you open the box, the atom, and therefore the cat, exists in a superposition of decayed, cat dead and not decayed, cat alive, and only collapses into one or the other the moment you open the box and look. It's usually presented as a puzzle, almost a horror, a cat suspended in some ghostly state between life and death. But in Everett's picture, there's no ghostly in-between state at all, and nothing especially horrifying happening. There's simply a branch where the atom decays and the cat dies, and a separate branch where it doesn't and the cat lives, both fully real, both fully definite, from the very beginning, neither one waiting around in some spooky, undead limbo for someone to look. In a strange way, Everett's interpretation answers Schrödinger's complaint quite neatly, even though Schrödinger himself never fully embraced many worlds as the answer. The absurdity Schrödinger was pointing at mostly comes from insisting there has to be one single collapsed outcome. Once you let go of that requirement, the cat stops being a paradox at all. It just becomes two definite cats, in two separate, non-communicating branches, neither one particularly strange within its own branch. Now, here's the human part of the story, and it's a genuinely sad one, and I think it deserves to be told slowly and gently, the way it actually happened. Everett brought this idea to his advisor, John Wheeler, who was intrigued, genuinely, by the elegance of it, but also nervous, because this was Princeton in the mid-1950s, and the physics establishment was still overwhelmingly loyal to the Copenhagen interpretation, largely because Niels Bohr himself, based in Copenhagen, remained one of the most towering, respected figures in the entire field, someone whose approval could make or quietly end a young physicist's career. Wheeler actually traveled to Copenhagen himself, in the mid-1950s, hoping to walk Everett's idea past Bohr directly, to get some kind of blessing, or at least to soften the impact of what he suspected would otherwise land as a direct challenge to Bohr's own framework. It didn't go well. Bohr and his close colleagues in Copenhagen were unimpressed, even somewhat dismissive, viewing the whole proposal as either a restatement of things they already understood or a needless complication of a picture they considered already settled. Wheeler came back from that trip and encouraged Everett to tone down the language of his thesis considerably before it was formally published in 1957, softening some of the more provocative claims about branching reality, adding cautious, hedging language, framing it as a variation on existing ideas rather than the sharp break it actually represented. It's a small, human detail, an advisor trying to protect a promising student from a field that wasn't ready to hear what he was actually saying, and it likely dampened the paper's impact considerably, right at the moment it needed to make its strongest possible case. The paper landed, essentially, with silence. It received almost no attention for over a decade. Everett, apparently discouraged and needing a stable income that academic physics wasn't offering him, left the field entirely shortly after finishing his doctorate and went to work for the Pentagon, doing classified defense analysis and operations research work related to nuclear strategy during the Cold War. He became, by most accounts, quite successful in that world and quite wealthy, but he never returned to physics as a career. It took until the early 1970s for anyone to really pick the idea back up seriously. A physicist named Bryce DeWitt, working at the University of North Carolina, came across Everett's old, largely forgotten thesis and became convinced there was something genuinely important buried in it, something the physics community had too quickly dismissed. DeWitt began writing about it himself, giving it a catchier, more evocative name than anything in Everett's own cautious, hedged 1957 paper, calling it the Many Worlds Interpretation, a name vivid enough that it finally started catching the attention of a wider audience of physicists and eventually, the public. DeWitt even wrote directly to Everett, by then working in his Pentagon defense job, to ask him about the idea. It's a strange image to sit with, a physicist reaching out, over a decade later, to reintroduce a man to his own most important discovery, one he'd mostly stepped away from and moved on from in his own life. Colleagues who knew Everett later described a man who smoked heavily, drank heavily, and grew somewhat cynical, watching from a distance as his old idea slowly began attracting more serious attention through the 1970s. Hugh Everett died in 1982 of a heart attack at only 51 years old, still largely outside the physics community he'd once been a rising part of. Per his wishes, his ashes were disposed of, without ceremony, in the trash, an oddly bleak detail that his own daughter later cited as a reflection of just how disillusioned he'd become. It's a strange thing to think about now. A quiet graduate student proposes that reality itself is constantly, silently branching into uncountable parallel versions every single moment, gets politely told to soften it, watches the physics community shrug it off for over a decade, leaves the field entirely, and only starts getting real recognition, real vindication, well after he'd already stepped away. Since then, the picture has filled in considerably and gotten more rigorous. A physicist named Wojciech Zurek helped develop something called decoherence theory through the 1970s and 80s, which explains, mathematically, why these different branches, once they split, effectively lose the ability to interfere with or communicate with each other almost instantly. Let's slow down on what that actually means, gently, because it answers a natural question, which is, if all these branches are real, why don't we ever notice them bumping into each other, the way overlapping ripples on a pond visibly interfere with one another? Decoherence explains that once a quantum system becomes entangled, with a large, complex environment, like a measuring device, or the air in a room, or a human brain full of trillions of particles, the different branches spread their influence out across so many particles so quickly that any meaningful overlap between them becomes, for all practical purposes, permanently undetectable. It's not that the other branch stops existing. It's that it becomes causally sealed off, almost instantly, the moment enough particles get involved, which is part of why we never bump into evidence of it in ordinary life. There's also an honest, still unresolved puzzle at the center of many worlds, sometimes called the probability problem, and I think it deserves to be named clearly rather than glossed over, because pretending every corner of this theory is neatly resolved would be dishonest. If every possible outcome definitely happens in some branch, with total certainty, what does it even mean to say one outcome is more likely than another? In ordinary quantum mechanics, we routinely calculate probabilities, say, a 70% chance an atom decays within some time window, and those numbers are tested constantly, matching experiment after experiment with remarkable precision. But if all outcomes always happen somewhere, in some branch, the usual, everyday meaning of probability gets slippery. Physicists like David Deutsch, and more recently Sean Carroll, have both worked seriously on this question, developing various technical approaches trying to recover ordinary probability from a picture where everything happens all the time. It remains one of the more genuinely unsettled corners of the theory, something honest advocates of many worlds will tell you themselves, rather than pretending it's fully resolved. That kind of honesty, admitting what still doesn't quite fit, is worth trusting more, not less, than a story that claims to have every loose end already tied up. I want you to sit with something for a moment, gently, before we move on, because this is the level of tonight's story that tends to land the most personally. If Everett's picture is right, then in this exact instant, countless branches are quietly splitting apart from this one. Somewhere, a version of you that decided to get up and do something else tonight instead of listening to this. Somewhere, a version of you that fell asleep 2 minutes ago. Somewhere, endless small variations, endless branches, diverging silently, forever, from every possible quantum event happening inside you and around you right now, none of them aware of each other, none of them able to reach back and compare notes. You'll never know which branch you're in, because from the inside, every branch simply feels like the only one there is. That's not a flaw in the theory. That's exactly what the theory predicts you'd experience, regardless of which branch turned out to be yours. There's one more piece of Everett's story worth telling slowly, because it adds an odd, almost poignant coda to the whole thing. Decades after his death, his son, Mark Everett, became a musician, the frontman of a band called Eels, and later made a documentary journey retracing his father's life and work, sitting down with physicists who explained, patiently, just how significant his father's rejected thesis had eventually turned out to be. It's a strange kind of posthumous vindication, a son learning, years too late for it to reach his father, that the idea Hugh Everett had been quietly dismissed for was slowly becoming one of the most seriously discussed interpretations of quantum mechanics among working physicists, alongside Copenhagen itself. Today, informal surveys of physicists show many worlds holding a substantial, sometimes plurality, share of belief among specialists in quantum foundations, a level of respect Everett himself never really got to see or experience while he was alive. Let's also gently address something that tends to unsettle people the first time they really absorb this idea, which is a worry about identity itself. If the universe is constantly branching, is there really a single, continuous you moving through time at all, or are you actually a new person, freshly generated, at every single branching moment, with only a kind of borrowed memory connecting you to whoever existed a moment before the split? Physicists who take many worlds seriously generally don't think this changes anything about your actual, lived experience. From the inside, every branch experiences an unbroken, continuous thread of memory and identity, exactly the way you're experiencing this moment right now, regardless of how many other branches happen to exist alongside it, unreachable, unaware of each other. The branching doesn't interrupt anything from where you're sitting. It just means the full picture, the one no single branch can ever see from the inside, is larger and stranger than any one thread within it. Let that sit there quietly for a second. We don't need to resolve it tonight. We're just visiting it. Let's move to the last level now, the strangest one, the one that sits right at the very edge of what most physicists are even willing to call physics anymore. This one belongs mostly to Max Tegmark himself, the physicist whose four-level map we've been quietly following all night. Tegmark is Swedish-American, a cosmologist who spent much of his career at MIT, working on very concrete, very mainstream observational cosmology, analyzing real data from real telescopes, alongside these much more speculative, foundational questions about the nature of reality itself. That combination is worth noting gently, because it means the same person organizing tonight's four-level framework has also spent decades doing hands-on, rigorously testable science, which is part of why his framework tends to be taken seriously even by physicists who ultimately disagree with its most speculative final level. He's someone comfortable moving between careful data analysis and genuinely open-ended philosophical speculation, without pretending the two are the same kind of activity. Tegmark laid this final idea out most clearly in a Scientific American article in 2003, and later expanded it into a full book in 2014 called Our Mathematical Universe. And the idea, at its core, is this. What if mathematics isn't just a language we use to describe reality, but is, in some deep sense, reality itself. Let's slow down, because this one is genuinely disorienting, maybe the most disorienting idea of the whole night, and it deserves to be unpacked carefully rather than rushed past. Most of us, even most physicists, tend to think of mathematics as a tool. A very good, very precise tool, but still just a description, a map, sitting somewhere separate from the actual physical territory it describes. The equation for gravity isn't gravity itself, we'd normally say. It's just our best way of writing down how gravity behaves. Tegmark's proposal flips that relationship. He suggests that any mathematical structure which is fully self-consistent, meaning it doesn't contradict itself, meaning its internal logic holds together completely, already exists, physically, as a real universe, somewhere. In whatever sense existing means for something that isn't made of atoms or energy the way we're used to. Our own universe, in this view, isn't described by mathematics. Our universe simply is a particular mathematical structure being experienced from the inside by things like us, made of parts of that same structure, capable of noticing the structure we're embedded within. Here's a way of holding on to this that might make it feel a little less abstract, even though the idea itself resists ever becoming fully concrete. Think about a story written down in a book. From outside the book, the characters are just ink patterns, marks on paper, nothing more. But if you could somehow shrink down and live inside the story, experience it from the inside, the way a character does, the ink wouldn't feel like ink to you at all. It would feel like weather and gravity and other people and time passing and a whole coherent, lived-in world, because the internal logic of the story would be the only logic you'd ever have access to from in there. Tegmark's suggestion is something like that, except without any author, and without any ink, and without anything external doing the writing at all. Just the internal logic itself, self-consistent, complete, and, if you happen to be built out of a piece of that logic capable of noticing its surroundings, indistinguishable from a genuine, full, physical universe, because from the inside, that's exactly what it would be. Here's the argument for why some serious physicists find this appealing rather than dismissing it outright. There's a real, long-standing mystery in physics, sometimes called the unreasonable effectiveness of mathematics, which is just this observation that abstract mathematics, developed by mathematicians often with no physical application in mind at all, keeps turning out, decades or centuries later, to describe real physical phenomena with almost eerie precision. Non-Euclidean geometry was developed as a pure, abstract curiosity long before Einstein needed exactly that kind of geometry to describe curved spacetime in general relativity. Tegmark's idea offers a strange kind of explanation for that eeriness. If physical reality simply is mathematics, rather than merely being described by it, then it stops being a coincidence that mathematics keeps fitting reality so well. Of course it fits. There was never anything else there to begin with. This mystery has a longer history than Tegmark's own work, worth pausing on gently. Back in 1960, the physicist Eugene Wigner wrote a well-known essay titled, plainly, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, in which he expressed genuine, honest bewilderment at just how often abstract mathematical tools, invented for their own internal elegance, with no thought toward physical application, kept turning out decades later to be exactly what physics needed. Wigner didn't offer a tidy explanation. He mostly just sat with the strangeness of it, calling it a gift we don't fully deserve or understand. Tegmark's mathematical universe hypothesis, decades later, is really one attempt at finally answering the question Wigner was content to leave open. Not everyone finds the answer satisfying, and that's fine. But it's worth knowing the puzzle Tegmark was responding to didn't start with him. It had been quietly sitting there, unresolved, for generations before he tried to address it directly. There's a related motivation worth mentioning here too, gently, connecting back to something we touched on earlier tonight with Weinberg's cosmological constant prediction. Physicists have long noticed that several of the fundamental constants of our universe, the exact strength of gravity, the exact mass of certain particles, the exact value of that cosmological constant, seem to sit within a surprisingly narrow range that allows stars, chemistry, and life to exist at all. Nudge several of these numbers even slightly, in either direction, and by most calculations, you'd get a universe with no stars, no chemistry, nothing resembling the kind of complexity capable of asking questions like the ones we're asking tonight. This observation is sometimes called the fine-tuning problem, and it's genuinely puzzling, regardless of which of tonight's levels you find plausible. One response, the one we already discussed with Weinberg, is to say there are countless universes with countless different values, and we simply had to find ourselves in one of the rare ones capable of producing us. Tegmark's Level 4 offers a particularly expansive version of that same basic move, suggesting there isn't just a large, but still finite landscape of possible universes, string theories 10 to the 500th, but in genuinely unlimited space of every mathematically consistent possibility whatsoever, guaranteeing that some among them, ours included, would inevitably land in a life-permitting configuration. I want to be honest and even-handed with you here, the same way we've tried to be honest about every level tonight, because this final level is where even many physicists who take levels 1 through 3 quite seriously start to get uncomfortable. Most working physicists regard Tegmark's mathematical universe hypothesis as closer to philosophy than to testable physics, and Tegmark himself has generally been open about that, framing it less as a confirmed scientific theory and more as a serious, carefully reasoned philosophical position, one worth taking seriously, but one that doesn't currently make specific, testable predictions the way Level I's cosmic horizon reasoning does, or even the way Level 2's cosmological constant prediction did. It's the softest, most speculative level of the whole 4-level structure, sitting right at the boundary where physics starts blurring into metaphysics. But even here, even at this outer edge, notice the same underlying pattern from earlier tonight. Someone took an observation that already exists, in this case, the strange effectiveness of mathematics, something physicists had quietly puzzled over for generations, and followed it a little further than most people are usually willing to go. Not further because the evidence demanded it, necessarily, but further because the internal logic, once you accept a few starting assumptions, seemed to lead there almost naturally. Let's bring these 4 levels together now, gently, because I think it helps to see them laid out side by side rather than as 4 separate, disconnected shocks. Level 1 says space itself, if large or infinite and roughly uniform, would eventually repeat every possible arrangement of matter somewhere far away, including, statistically, arrangements resembling this exact room, this exact moment. Level 2 says the process of cosmic inflation may never fully stop everywhere, endlessly generating separate bubble universes, each one possibly settling into a different version of physics itself, out of an almost unimaginably large landscape of possibilities. Level 3 says quantum mechanics, taken completely literally, without inventing a special collapse rule found nowhere else in physics, implies reality is constantly, silently branching into countless divergent versions with every uncertain quantum event. And Level 4, the strangest and most speculative, suggests that any fully self-consistent mathematical structure might, in some sense, simply exist as its own universe, meaning ours might be just one mathematical possibility among an inconceivably vast landscape of others. Here's what I want you to really notice, though, more than any single one of these levels on its own. These 4 ideas didn't come from the same place. They weren't built by the same person or even the same generation, chasing the same goal. Level 1 comes out of straightforward cosmology and geometry. Level 2 comes out of particle physics and inflationary theory. Level 3 comes out of the foundations of quantum mechanics, a completely different corner of physics with almost no direct connection to cosmology at all. And Level 4 comes out of a philosophical question about the nature of mathematics itself. For separate roads, walked by different people for different reasons, none of them setting out looking for parallel universes, and all 4 of them, independently, kept bumping into some version of the same strange idea. That's really the heart of tonight's whole story. Not any one level being definitely true. Just how often, and how independently, physics keeps stumbling into this same general neighborhood. And I want to be clear, gently, that you don't have to accept all 4 levels together as some kind of package deal. They're independent. You could find Level 1's reasoning about infinite space fairly convincing, since it rests on relatively modest, well-tested assumptions, while remaining much more skeptical of Level 4's mathematical universe idea, since it currently offers little in the way of testable predictions. That's a completely reasonable position. Plenty of physicists hold exactly that kind of mixed view, taking some levels seriously and treating others as interesting philosophy. You're allowed to do the same. You're allowed to believe in one of these, or all four, or none of them at all, and still walk away from tonight having understood something true about how strange and how surprisingly consistent modern physics has turned out to be. There's also a quiet, nested relationship between these levels that Tegmark himself has pointed out, worth mentioning gently before we move on. Each level, in a certain sense, contains the ones before it. If level 2 is true, and there really is an eternally inflating background spinning off countless bubble universes, then each of those bubbles, including our own, would presumably still be subject to level 1's reasoning internally, an enormous, perhaps infinite, expanse of space within each bubble, capable of its own internal repetition. And if level 3 is true, and reality really does silently branch with every quantum event, then that branching would presumably be happening inside every single one of those bubbles, across every one of those repeating regions, multiplying the strangeness further still. The four levels aren't necessarily four separate, competing claims about the same single question. They may simply be four different scales at which the same basic pattern, more existing than we can directly see, keeps showing up, each one nested quietly inside the one before it, like a set of increasingly enormous rooms, each containing the last. Let's talk honestly, for a few minutes, about evidence, because that word matters, and I don't want to leave you with the impression that any of this is just speculation dressed up as science. Some of tonight's ideas do make testable predictions. Others, honestly, mostly don't, at least not yet, and it's worth being clear about which is which. Level 2, the bubble universe picture, does offer one genuinely testable prediction, even if it's a difficult one to check. If our universe really did form as one bubble inside an eternally inflating background, and if other bubbles occasionally formed nearby, close enough in that vast inflating space to have collided with our own bubble at some point in the distant past, that collision should, in principle, have left behind a faint, specific kind of imprint on the cosmic microwave background, the ancient afterglow of light from the early universe we mentioned earlier tonight. Let's slow down on why a collision like that would even leave a mark at all, because it's a nice piece of reasoning in its own right. If two bubble universes brushed against each other early on, the collision would locally disturb the density and temperature of the material inside each bubble along the boundary where they touched, slightly more in some directions than others, creating a subtle asymmetry. That asymmetry, the reasoning goes, would still be faintly imprinted billions of years later, as a specific kind of roughly circular disc-shaped pattern in the cosmic microwave background, distinguishable, in principle, from the ordinary, more randomly distributed temperature fluctuations you'd expect from ordinary early universe physics, without any collision at all. Physicists including Stephen Feeney, Matthew Johnson, and their collaborators, working around 2010 and 2011, actually searched for this signature directly, combing through detailed maps of the cosmic microwave background produced by the WMAP satellite, looking for these faint circular patterns, sometimes described informally as cosmic bruises. It's a real search, using real data, looking for a real, specific, falsifiable prediction, exactly the kind of test a scientific idea is supposed to be able to survive or fail. The results, so far, have been inconclusive. A small number of candidate patterns were flagged as worth further investigation, but none held up as a confident, statistically robust detection once scrutinized more closely. No confirmed detection, but also no definitive ruling out either, which is an honest, if slightly unsatisfying, place for the evidence to currently sit. It's important to be fair about the criticism here too, the same way we were with level 2 earlier tonight. Physicists like George Ellis and Joe Silk co-wrote a widely discussed piece in the journal Nature in 2014, arguing, publicly and pointedly, that too much of modern cosmology, particularly around the multiverse and the string landscape, risks drifting away from traditional scientific standards. Their concern wasn't simply that these ideas were strange, plenty of confirmed physics is strange, but that a landscape of 10 to the 500th possible universes can seemingly accommodate almost any observation you could make, which threatens to turn multiverse theories into something that can explain everything and therefore, in the strict scientific sense, predicts nothing in particular. Ellis and Silk called for cosmologists to hold these ideas to the same standards of testability as the rest of physics, rather than letting their mathematical elegance alone stand in for genuine evidence. Defenders of the multiverse picture, including some of the physicists we've mentioned tonight, have pushed back on this in turn, arguing that a theory doesn't need every one of its individual components to be independently testable, so long as the overall framework it emerges from, in this case, inflation and string theory, was arrived at through ordinary, testable physics in the first place, and continues to make some testable predictions, like Weinberg's cosmological constant prediction, even if other parts of the picture remain currently untestable. It's a real, ongoing tension within physics itself, not a settled debate, and it's one worth being honest about rather than glossing over. Levels 1 and 3, meanwhile, don't really offer new observational tests of their own, so much as they follow logically from things we've already measured quite carefully: the flatness of space for level 1, and the mathematical structure of quantum mechanics itself for level 3. And level 4, as we discussed, currently offers essentially no testable predictions at all, which is exactly why most physicists file it under philosophy rather than physics. It's worth mentioning, too, gently, that the search for bubble collision signatures hasn't stopped just because the early searches came back inconclusive. Newer, more sensitive maps of the cosmic microwave background and next-generation ground-based observatories currently being built specifically to map that ancient light with far greater precision than WMAP or Planck ever could, continue to offer at least the possibility of revisiting this search with sharper tools someday. It's slow, patient, decades-long work, the kind that rarely produces a dramatic headline, just steadily improving maps, built instrument by instrument, year by year, gradually narrowing down what can and can't still be hiding in that ancient light. That's really the honest, appropriate place to leave Level 2's evidence sitting tonight. A real, specific, falsifiable prediction, genuinely searched for using real data, currently inconclusive and not yet closed off either way. Science, done honestly, is often exactly this: unglamorous. Not a dramatic confirmation or a dramatic refutation, but a careful, ongoing search, sitting patiently in an unresolved middle state, waiting for better data. So, where does that honestly leave us? Not with certainty, not with proof, but with something more interesting than either certainty or nonsense, which is a set of ideas that emerged naturally, almost unavoidably, from taking well-tested physics completely seriously and following its logic a little further than we're usually comfortable going. Let's come back, now, gently, to where we started tonight. Your breathing. This room. This exact, particular moment. We've traveled a long way from there, through endless beaches of repeating space, through boiling pots of bubble universes, through a quiet graduate student's branching realities, all the way out to the edge where physics starts to blur into philosophy. And now we're settling back down again, right where we began. Here's what I hope you take with you into sleep tonight. More than any single fact about inflation or wave functions or mathematical structures, every single one of these strange ideas we walked through came from somewhere ordinary. Somebody took equations that had already been tested, already been trusted, already been quietly relied upon for other purposes, and simply asked, patiently, what happens if we follow this a little further than usual? That's it. That's the whole method behind every level tonight. Not wild invention. Just careful people, taking careful math, seriously, further than most of us ever think to. And maybe there's something quietly comforting in that, even if the ideas themselves are unsettling. The universe isn't hiding some deliberately confusing trick from you. It's just larger and stranger and more layered than our intuitions were ever built to expect, built as they were for a much smaller, much more local kind of life. Feeling confused by all this isn't a sign you've missed something. It's a sign you've understood exactly how strange this material actually is, which is the correct, appropriate response. The same response some of the smartest people who ever lived also had, sitting with these exact same ideas. You don't need to resolve any of it tonight. You don't need to decide which level you believe, or whether you believe any of them at all. You can just let it settle, the way sand settles at the bottom of still water, slowly, without any hurry. Somewhere, maybe, impossibly far across an endless beach of repeating space, or in some bubble drifting elsewhere in an eternally inflating background, or in some branch splitting quietly away from this exact instant, or in some other mathematical structure entirely. There might be another version of this moment, another version of this room, another version of you. Think, for a second, about how strange it is that any of this got discovered at all. Edwin Hubble, patiently measuring the flickering brightness of a single distant star. Alan Guth, underlining a private thought in a notebook, calling it spectacular before anyone else had a chance to agree with him. A quiet, discouraged graduate student, writing a thesis that got softened before it was even published, then walking away from physics entirely, never quite knowing how right he might have been. Each of them just followed one honest thread of reasoning as far as it would go, without needing to know, in advance, where it would end up, or whether anyone would believe them. That's really all any of tonight's ideas are. Honest threads, followed patiently, by people willing to sit with not knowing for a while. None of them had tonight's whole picture in front of them while they were working. Hubble never knew about Everett. Everett never lived to see how seriously his own idea would eventually be taken. Tegmark's four-level map, the very structure we've used to walk through all of this tonight, wasn't assembled until decades after most of these individual discoveries had already been made, separately, by people who mostly never worked together or even overlapped in time. The map came afterward, quietly stitching together threads that had been laid down independently by people who couldn't have known, at the time, that their small, careful piece of work would someday sit alongside three others, forming something that looks, from a distance, almost like a single coherent story. You're allowed to sit with not knowing too, tonight. You don't owe these ideas a verdict. You don't owe yourself certainty before you're allowed to rest. Uncertainty isn't a problem to be solved before sleep is permitted. It's just the texture of what's actually true here, the honest shape of how much we do and don't understand, and it's a perfectly fine, perfectly comfortable thing to fall asleep inside of. So let your attention loosen now. Let it drift off these ideas the way it drifts off everything else at the end of a long day. Not because the ideas stopped mattering, but because you don't have to hold on to them anymore tonight. Let the beach stay out there, endless and quiet. Let the bubbles keep rising, slow and unhurried, somewhere far outside anything you'll ever need to think about again before morning. Let the branches keep splitting, gently, without you having to track a single one of them. Let the mathematics keep being whatever it already is, with or without your attention on it. But right here, in this branch, in this bubble, in this patch of an endless beach, whichever one it turns out to be, it's late, and your body knows what it wants to do next. So let it. Let your thoughts get looser and slower, less interested in following any particular thread all the way to the end. The ideas will still be here. They'll wait, patiently, the way they've been waiting for centuries already, for whenever you're ready to come back to them. Sleep well.